The infamous two-sum, the meme problem at this point. It's super popular. In my opinion, the only one company has not banned it, and the reason they haven't banned it is because you are supposed to embrace the cognitive dissonance and embrace the lie that is working there. They shall remain nameless, but I have been asked this question in an interview before. Given an array of integers and target value, return the indices of two numbers such that they add up to the target. Each input has exactly one solution, and return the answer in any order. All right, so let's talk about target runtime and space complexity. We've got some input. It's an array. This first example looks like it's sorted, but this second one is not. And there could be some repeats on the input. All right, so since it's unsorted, we're probably expecting a linear runtime because we have to touch on everything at least once. So what about space complexity? Can we this follow-up question, can you do it in less than quadratic time complexity? Yeah, the solution is actually linear complexity. Quadratic would be the dumb brute force solution, which, okay, honestly, like, you can get away with constant space if you did it in quadratic time. But if you say add linear space, that's how you get it down to linear time. So I guess there is that bit of trade-off from there. Let's talk about it. The quintessential solution is to make a hash map so that and you store it such that the keys are the numbers from the nums array and the values are the indices. The reason being you can if you assume constant time lookup for the keys, which it's going to be a hash-based hash map. If you assume constant time lookup, then that's how you get away with the linear time complexity. Now, okay, if you've ever taken a algorithms class, your professor will slap you in the face if you tell them that hash lookups are constant time. In the real world, they're like amateurized constant time, and there's a lot of like proofs and engineering that have gone into designing these hash functions. A good cryptographic hash function is going to have, I think, at most like 2 in 2 to the 60th. So 2 over 2 to the 60th chance of a collision. This number, 2 over 2 to the 60th. That's a pretty tiny number. And that is your kind of upper bound on the chance of collision of a hash-based function. A lot of money has been out and available as a bounty for finding collisions on a lot of like common hash functions. So like the real chances of a collision are, for practical purposes, at this point impossible if you use the right hashing function. And if you find yourself with collisions, well, the language is just going to adopt a different hash function. So let's go ahead and start actually coding. In C++, hash maps are under the header unordered map. Specifically, you want to use unordered. If you just use a regular map like this, that's going to be ordered. And the way it's ordered is by using a tree under the hood. I think a red-black tree, something. It's tree-based, meaning, there we go, spelled it right. Meaning that lookup times when you try to retrieve an index from, so it's going to be logarithmic. Don't do that. That would turn your runtime into n log n instead of n times constant, which gets you just regular n. So let's keep going, I guess. All right. First, we'll go ahead and declare our map. So unordered. And it's going to take, so the keys are going to be integers because they're going to be values from this array. And the values in this map are going to be also integers because we're going to store the indexes. So I'm going to call it, I guess, T for table. I don't know what to call it. T is a decent convention. It's not bad. And then we need a main loop. A main loop that does what? So it's going to be a for loop. And it's going to go, we need both the values and the indexes as we go through the array. So just going to use a classic standard for loop. Int I equals 0, I is less than num size. Come on. And then we need a final return statement. So we're going to return. What I'm going to do is if there's a match found inside this loop, I'll just return right away. And if there's not a match found, I need a return statement just so that this will compile at all, but hopefully we never hit it, assuming there is a solution in every input, but it's going to be, and it's going to be this. Some negative indices. This would be like an error, meaning we never found it. And then if you use braces, the nice thing is you don't have to actually like declare a vector and give it values. You just, this will resolve to it by the compiler. That's fine. All right, so what do we do here? First, we're going to check if we've seen a number. Okay, the other key to understanding this algorithm is when given a number, so we're looking at a particular value within nums, how do you know what you need? Well, simple subtraction. So for example, we have, I'm going to declare another variable for this loop. Doesn't matter if it doesn't really need a value to start out with. So m is equal to target minus nums I. What value would we need, hypothetically, in order to add up to our target value with our current one? And then we're going to check if that's in our hash map. So if t.find m not equal to t.end. So what this is doing, this looks like it might be a linear time search. It's given that it's unordered, it is going to be constant, hopefully, because of the hashing. If it's, you know, some other data structure, it might be some other runtime. The syntax is the same, but this is looking through the keys for this value, and if it's not found, it returns an iterator that points one past the end of like the list of keys. And if it is found, it returns an iterator to that instead. But we're just checking to see if it's present. We don't actually need the iterator. We just need to know if it's there. So if we find it, then we're going to go ahead and return. What do we return? We return our current index, and we return the index of this hypothetical value, which we have stored in our table. Haven't actually written that storage statement yet, but it will, yeah, that should do it. And then otherwise, if it's not in our table, we need to add the current number. So this m is a hypothetical, but we need to add the real number to our table now. So t of nums of I is I. Oh my gosh, there we go. And I think that'll do it. So I'll go ahead and check out runtimes for certain things. So we're at linear space. So our overall runtime is O of n time and space. And I do recommend writing out some of these things for your interviewer, so that way they're not trying to remember, you know, after you hang up the call, like, oh, did we cover that or this, or did they hit the space? If it's written down, there's no denying, because any sort of large company worth their salt, or any company worth their salt, is going to save the interview code that you wrote on the file along with their comments and justifications. So if this is there, there's no denying that you covered runtime and space. And the time is, all right, this is our linear space. This is the thing that we potentially add an entry for every element. Worst case scenario, the two that matches that add up to our target are the very last two elements, and we have to go through the whole loop, meaning we have to add an entry for every single item in the loop to save off the index, and then to, you know, find our actual solution. All right, now let's do an example. Let's step through it. Let's do it. I'm going to do, I think, this one because it's a little shorter, and I think it illustrates the process a little more nicely. Because this one, yeah, if it's 0, 1, it's going to exit early, and the rest is kind of irrelevant. It's this one where, like, and it'll go through the whole example. It shows that things are kind of out of order, so I think that'll show it better. All right, so our input is this. And then we've got our hash map. All right, what are we doing? So let's go and start. Declare our table. That's what this is. It's empty right now. For I in 0 through the numbers, the size of the number array. And we have our m value. So m is what? M is gonna be, so our target is, what is our target? 6. So if the target is 6, then M is, where is it? Target minus the current number, 6 minus 3. So M is 3. Have we seen 3? No, our table is empty. So we're going to add 3 to our table. 3 is at index 0. All right, next iteration of the loop. M is going to be 6 minus 2, so 4. M is 4. Have we seen 4? No, there's no key in our table for 4. So we're going to add it. 4 is at 1. Next iteration, we're looking at 4. So if our target is 6 minus 4 is 2. M is now 2. Wait, am I doing this math right? 2, 4. Oh, wait. Take a step back. I wrote it down wrong. We were adding 3 and then 2. Yeah, okay, this is right. We saw 2 at index 1. Yeah, that was a mistake in the mental example, not in the algorithm itself. All right, so now, our M is 2. Going back to the final iteration where we're looking at this, 6 minus 2 is 4. 6 minus 4 is 2. Oy, oy, oy. And look, oh, look at that. We've got 2 in our hash map. It is a key that exists. We have found it. It is there. All right, so we're going to break out early. We're going to return. So I is currently 2, and then our current number, the index of our current number. Wait, we are currently at I, and then T of M. So T in here, 1. So we're going to return 2, 1. Is that our expected solution? Yeah, it's in the opposite order, but that's fine. That works just fine. All right, cool. I think that'll do it. Let's go ahead and give it a run for syntax. Oh no, what'd I do? M equals, okay, unqualified. Maybe if I just give it a value. Oh no, you know what it is. There. That was declaring these in the same statement. I just want a variable that exists inside the context of the loop, and so I didn't need that extra int declaration. Hoi do hoi. Cool, cool. All the examples are working. And submit it, and boom. Let's go ahead and mark it off. Good night.